Welcome back, my dear students, in part 2 of Chapter 5 Sound Energy. At the end of this part, you will be able to determine the sound intensity at a point and define the threshold of hearing and the threshold of pain. But before, let's remember the main points of the previous part. First, sound carries energy known as sound energy or acoustic energy. Second, the acoustic power P of a transmitter is the energy it provides to the surrounding environment per unit of time. It is given by P is equal to E divided by T. Third, in the case of a sinusoidal sound wave, the power is proportional to the square of the amplitude. P is equal to Ka squared. When moving away from a sound source, the sound received is weaker. Why do you think this happens, and how does physics explain this phenomenon? To explain this phenomenon, we will consider first a point source O, emitting sound in all directions of power P. Remember that the power is the energy emitted per unit time. In our study, we will consider these conditions. First, sound propagates with the same speed in all directions. Then, the wavefronts necessarily take the same spherical shape as you can see in this figure. Second, the medium is considered non-damped, so the power emitted by the source is conserved. That means each wavefront will receive the same power P. And this power is distributed uniformly over the surface area of the spherical wavefront. But what does it mean that the power is distributed evenly or uniformly over the surface area of the spherical wavefronts? To understand this better, we consider a single sphere having radius r2 and surface area s2, receiving the power completely from the source. If the sound receiver occupies half of the sphere as shown here, then it will receive half of the power. If SR is equal to S2 divided by 2, then PR, which is the received power, is equal to P, which is the emitted power, divided by 2. If another receiver occupies a quarter of the sphere, then it will receive quarter of the power. We deduce that the ratio of the receiving surface area to the total surface area is equal to the ratio of the received power to the total power. This equality of ratios certainly reflects the triple rule, such that if S2 receives P, so SR receives PR. Knowing that the area of the sphere of radius r is equal to A is equal to 4 pi r squared, then the area of S2, which has a spherical shape as we have mentioned before, is equal to 4 pi r2 squared. Therefore, the received power is calculated using PR is equal to SR times P divided by 4 pi r2 squared. After explaining the uniform distribution of the emitted power, now let us consider the following experiment. Two identical microphones A and B are placed at the same distance or same radius from O. In other words, both are placed on the same sphere of surface area as 2. Do you think that they receive the same loudness? Yes, of course, that's logic. We say that these two microphones receive the same intensity of sound because they are at equal distance from the source. Consider now another two microphones C and D, where the microphones A, B, C, and D are all identical. But notice that the intensity received by C is greater than the intensity received by D. Why? Simply because C is closer to the source. So, as you have seen that a new physical quantity is defined by physicists, which is called the sound intensity or the acoustic intensity. The intensity is defined by the power received at a certain point per unit area held perpendicular to the direction of propagation of the sound wave. First, the sound received by the two microphones A and B, having the same surface area and placed at the same distance from the source, are equal because they receive the same portion of the power. Remember that the power is distributed uniformly. Then PA is equal to PB. Now, applying this relation of the intensity, we will get IA, which is equal to PA divided by S, is equal to PB divided by S, which is equal to IB. This result is consistent with the experiment done before, so this formula is still now valid. Now, let us examine it on the microphones C and D. The microphones C and D have the same receiving surface area, but D is farther from the source. The power P distributed over S2 is greater than S3. Then, the part received by the surface area of D is lower than that of C. Therefore, the power received by C is greater than the power received by D. PC is greater than PD. If we want now to find the intensity, then IC, which is equal to PC divided by S, is greater than PD divided by S, which is equal to the intensity at the microphone D. Again, this result is in agreement with the experiment, and this relation succeeds once again in explaining the phenomenon. In SI unit, the power is expressed in watt, the surface area in meters squared, and the intensity in watt per meter squared. Note, in this experiment we have used the microphone, which is very similar to the human eardrum. It has a receiving surface area S. After defining the intensity, now let us see how does it vary when moving away from the source. For this sake, we consider a point source emitting a sound of power P. Notice that as we move away from the source, the power spreads more widely and the intensity decreases. For example, at a distance of 2r from the source, the area increases by a factor of 4 and the new intensity is I divided by 4. At a distance of 3r, the intensity decreases to I divided by 9. Let us now solve application number 2. A point source emits a sound wave of power P is equal to 2 watts. At distances D1, which is equal to 4 meters, and D2, which is equal to 8 meters of S, the sound power is distributed over two spheres of respective areas. A1 is equal to 201 meters squared and A2 is equal to 804 meters squared. Part 1. Determine the intensity of the sound at each distance D1 then D2. Part 2. Verify that when D2 is equal to 2D1, then I2 is equal to I1 divided by 4. Please try to solve this application first alone, then check the solution. In part 1, A1 is equal to the power emitted by the source divided by A1, which is equal to 2 watt divided by 201 meters squared equal to 0.0099 watt per meter squared. I2 is equal to 2 watt divided by 804 meters squared, which is equal to 0.00248 watt per meter squared. In part 2, the distance D2 is equal to 8 meters, which is equal to 2 times 4, which is equal to 2D1. I2 is equal to 0.00248 watt per meter squared, and I1 is equal to 0.0099 watt per meter squared. Therefore, I2 is equal to I1 divided by 4. Application 3. A point source emits a sound wave of power 2 watt. A microphone of surface area SM is equal to 20 centimeters squared is placed at a distance R is equal to 20 meters from the source. Part 1. Determine the power received by the microphone, and Part 2. Determine the sound intensity received by the microphone. Again, please try to solve this application first alone. Part 1. The power received is equal to the power multiplied by the surface area of the microphone divided by 4 pi r squared, which will give 8 times 10 to the power minus 7 watt. In part 2, the intensity is equal to the received power divided by Sm, which will give 4 times 10 to the power minus 4 watt per meter squared, or we can use that I is equal to the power emitted divided by 4 pi r squared, which is equal to 4 times 10 to the power minus 4 watt per meter squared. Notice here that we have used that 1 centimeter squared is equivalent to 10 to the power minus 4 meters squared. It is known that the human ear has certain hearing limits concerning the frequency at which sounds of frequencies between 20 Hz and 20,000 Hz are heard. However, the ear does not hear sound if its intensity is lower than a value called the threshold of hearing, and it begins to feel pain if the sound intensity exceeds a certain value called the threshold of pain. The threshold of hearing I0 and the threshold of pain Imax vary with the frequency, person, and his age. For a frequency of 1000 Hz, the standard values are: threshold of hearing I0 is equal to 10 to the power minus 12 watts per meter squared, and the threshold of pain I is equal to 1 watt per meter squared. Let's solve application number 5. The sound intensity is 2 watts per meter squared at a distance of 3 meters. We have to calculate the minimum distance from the source without causing hearing damage, knowing that the threshold of pain is Imax is equal to 1 watt per meter squared. I1 is equal to the power emitted divided by 4 pi R1 squared, and I maximum is equal to P emitted divided by 4 pi R squared minimum. When finding the ratio of these two equations, then it will give I max divided by I1 is equal to R1 squared divided by R minimum squared, so 1 over 2 is equal to 3 squared divided by R squared, therefore R minimum will be equal to radical 18 meters. Let us now sum up the main ideas of this part. 1. The sound intensity is the sound power received per unit area placed at a point. It is given by I is equal to P divided by 4 pi R squared. 2. The sound intensity at a point is the sound power received per unit area perpendicular to the direction of propagation of the sound at the given point. I is equal to the power received divided by the surface area, which is PR divided by S. 3. For a frequency of 1000 Hz, the standard values are: threshold of hearing I0 is equal to 10 power minus 12 watt per meter squared, and the threshold of pain is I is equal to 1 watt per meter squared. It is very important to re-watch this video another time. Thank you for watching.